Hi, we are continuing discussing timings for latches and flip-flops. And this mini lecture I will be dealing with T-type flip-flop and latches. And the timings are exactly the same as in the case of D-type flip-flop, and instead of D, you've got a T input. And let's recall the operation of T-type flip-flop or latch is the following. If there is 0, no change on Q. If there is 1 on T, it toggles its state. It simply invert its state on Q. And as in the previous cases, we start with flip-flops, and the rising edge is the first one. And the initial state of the Q is 0, so we start drawing here at the 0 level. We must stop and decide to change or not to change. 0 on T means don't change its state. 1 on T, change to the inverted one. Yes. Change again, and no change here. And this is the first case for rising edge triggering. Falling edge, you should stop at green edges, which are falling edges are here, 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 and here, and you do the same as before. Start with 0, stop at first edge. Look at T, T is 1, so it toggles its state. Next, edge, active edge, 0, 0 doesn't change its state. 0 again, don't change and don't change until the end of the timing. And so quite different, yeah, because of the different time points when it can change its state. And the more interesting will be latches, more interesting and problematic a little bit, because I will show in a moment. If you start your analysis here with Q equal to 0, you must stop at the beginning of the activity periods. Activity periods are when these, you've got 1 on CK, and in these periods the flip-flop, the latch is allowed to operate according to the rule I've mentioned. So let's begin with the initial, at the beginning of this period there is 0, so no change until this change on T. This change tells us that you must change the value toggle, and you can do it again because it is still active, so you will have many toggles, they are oscillations, unwanted. Okay, it is not very useful, rather not useful at all. And what about the end? What's the last state? You simply don't know it. So you can stop, or you can maintain 1, or alternatively you can maintain 0, because you don't know how many toggles will be within the activity periods. So let's suppose that the last state on this edge, when the activity is finished, will be 1. Okay, and 1 will be maintained until the beginning of the next activity, when you have as well 1. So you will see, you will have the oscillations, and again you must decide this arbitrary choice what will be the static state when on this edge, when the T changes from, or changed from the 1 to 0. Okay, again, please. Hi, we are continuing timing analysis for latches and flip-flops. And this mini lecture I will be dealing with T-type elements, and let's start. The assumption for the initial condition is the same. Initial state of Q is 0. And we've got the timing for the changes which occur on T input and CK clock input. And our task is to draw the timings for 4 cases, 2 for flip-flops, rising edge triggered, falling edge triggered, and for latches, high level triggered and low level triggered. To recall, the operation of T is the following. When T is equal to 0, no change on Q. When T is equal to 1, there is a change to the inverted state. Okay, it toggles its state simply by invert the current state. And let's start with 0. And for the first, you must stop with at each rising edge and read the value of T. And there's 0, you don't change the state of Q. If there is 1, you change to the inverted one, and again there is a change, so you change to inverted signal, and no change because T is equal to 0. And this is the first case. In the second case, you must stop at green edges, which are falling edges. Okay, it is this case, falling edge triggered. You start with the same 0 signal. Now you read out the T. T is 1, so you must change the output. In the second, in the following edge, you've got 0, so you don't change anything. Again, 0, no change, and again 0, no change until the end. Okay. More interesting case when you've got the period of time, periods of time when there is possible to toggle its state, and it could occur many times within this period. So the oscillations will be visible on the output device, the device output. So let's start with 0 as in the previous cases. Let's mark the activity periods, active periods, when it can change its state to the inverted one. You must stop at the beginning of each state and then looking at T until the middle, yes, until the center of this period. No change will be visible, but starting from this point of time, you must toggle to inverted, and then it is still active. So it toggles many times within these periods until the end of this period, the activity periods on this edge. Now, what's the last value? We don't know how many oscillations were within this period, so it is our arbitrary choice to, let's say, end with 1. The alternative way would be, correct way would be to draw 0 level here. And you go to the next activity period and you do the same. Analyze T is equal to 1, oscillation will be present until the end of T equal to 1 equals 0 means no change. And of course, the end of activity is also no change, means also no change. And then the situation will repeat, because here you've got also T equal, and your choice is either or. Let's decide now that 1 will be present on the output until this. You must maintain this in between because it is not active. And then it is not active, no change, because T is 0, and starting from this, T is 1, so it toggles many times, and the toggles stop let's say, and we will have 0. And of course, it is our choice. Here you can have alternative state, which can be 0 or 1. So many different possibilities, because we cannot control how many changes occurred within these periods. Okay, so the last case is quite similar. Now we must look at these periods of time when there is low level. It is low level triggered, and we do similar analysis. T is 0, no change, and no active. T1 oscillations, and until the end of activity. If it's not active, it cannot change. We maintain it is arbitrary choice. Then the activity starts here, but until this point in time, no change occurs because T is equal to 0. Now oscillations, many toggles, and then stop because the activity finished, and then the activity, but T is equal to 0 within all the whole period of time, so no change will occur. And the last activity is also within this activity, T is also 0, so no change at all. That's the last case. So looking at these timings, they are quite different, okay? Comparing to the STE, STT, STD, which are the same for all 4 cases, variants of this 1-bit memory. Thank you.